All right, and in this video we'll talk about domain, evaluating piecewise functions, and simplifying difference quotients. When we look at shortcuts for finding the domain of functions, just remember that all polynomials have a domain of all real numbers. And remember, polynomials look like this, where we have natural number exponents. So we can't have negative exponents, we can't have fractional exponents, so that's what a polynomial will look like. We have rational functions, so this is rational, where we have a polynomial divided by a polynomial, and the denominator cannot be 0. So we just have to find out, is the denominator ever equal to 0? And if it is, then that x value is not in the domain. Then we have radical functions. So here's a radical square root of some function, and we know that this cannot be negative, or else we'll have an imaginary number. So we know that the inside of the radical, called the radicand, must be greater than or equal to 0 if we have an even root, like a square root, a fourth root, a sixth root, and so those are some shortcuts to finding domain. Let's see if we can do 3 of them. Alright, so we identify this as being rational, and that means we need to look at the denominator. This is rational, so we want to know, when is the denominator equal to 0? And we can factor like this. Multiply to get negative 40 and add to get negative 3, so we have x minus 8, x plus 5. The denominator equals 0 when x equals 8 and when x equals negative 5. So we have a domain that excludes 8 and negative 5. So the domain is negative infinity to negative 5, not including negative 5, union negative 5 to 8, not including 8, union 8 to infinity. And that's how we can write the domain in interval notation. All right, the next one, we have a radical function. So when you identify it as radical, now you're starting to focus on the strategy of finding out when the radicand is non-zero. So let's just look at some numbers here and get an idea of what's happening. So we want to choose x values and see if this is greater than or equal to 0. So if I choose 1, 6 minus 1 squared, that is greater than or equal to 0. 2, 6 minus 2 squared, 6 minus 4 is greater than 0. 3, 6 minus 3 squared, 6 minus 9 is negative, so that's not in the domain. 3 is not in the domain. And if we keep going, what if we try some negative numbers? Negative 3, 6 minus negative 3 squared, 6 minus 9, that's negative. It's not in the domain. negative 2. 6 minus negative 2 squared. 6 minus 4 is positive, and that is in the domain. So let's see what we have. The numbers that we want to keep are 1, 2, 3 is no, negative 2, so negative 2 works, negative 1, 1, 2. 3, negative 3 and 3 don't work, 0 works, and then we can have all the real numbers between there. So the question is, where does the domain end before you get to negative 3? Somewhere between these two, and what we're looking for is the change from positive to negative, which is going to be 0. When does the radicand equal 0? So we can solve this, and we have x equals positive or negative radical 6. So radical 6 must be between 2 and 3, so that means here at positive radical 6, over here at negative radical 6, those are the endpoints of the domain, of the interval that is the domain, and we have to consider, should we include negative radical 6 and radical 6 in the interval? So that means, do we use parentheses or a bracket? Well, we know that radical 6 makes the radicand equal to 0. Is it okay to have a 0 as the radicand? And it is okay. That means we can include negative radical 6 and radical 6, and that's the domain. So if you have a problem, if there's a function that's a little confusing, just make a table and it can help you narrow down your choices. So in the next one we have radical and rational. Rational and radical. We know that this can't be 0 and this can't be 0, and also the radical cannot be negative. So let's look at, we want this radicand to be non-negative, so we want it to be 0 or positive, but then it's in the denominator, so we don't want it to be 0. We want it to be greater than 0, and x plus 3, we want it to not equal 0. All right, so if I look at x is greater than 1, that means we're doing that. Here we have negative 3. We don't want negative 3, but it can go either way. So now if we put these on the same number line, we want them both to be true. So if we have negative 3, 1, the 1 is going to go like that, negative 3 goes like that, and we need to find out the numbers that are in both sets. So here we have 0. Is 0 in both sets? No, it's only in this one. How about 2? Is 2 in both sets? Yes. So that means we're going to start at 1 and go to the right, because these numbers are in both sets. These numbers are only in the one set. So we're starting at 1 and going to infinity. 1 cannot be included because of this set, so 1 is not included. All right. Pause the video and find the domain of these functions. So here we see that it is rational, and that helps us focus on the strategy of just finding out when the denominator equals 0. So we know that 1 is not in the domain, and so the domain is negative infinity to 1 and 1 to infinity. This is radical. That means our strategy is we want the radicand to be greater than or equal to 0. So x is greater than or equal to 3, 3 to infinity, including 3 is the domain. And it's a polynomial. So that means the domain is all real numbers automatically. We just have a nice shortcut there. Alright, so that's domain. Let's look at evaluating piecewise functions. And let's find f of negative 3 and f of 3. Okay, so this is one function that's made up of 3 different pieces of other functions. So let's think of where these are evaluated. To the left of 3, to the right of 8. To the left of 3, we're going to use this. Between 3 and 8, we're going to use this. To the right of 8, we're going to use this. And then we just have to see where on the number line is this x value. That'll tell us which function or which piece to use. So negative 3 is over here. That means we use this piece. And we're going to have 12 plus 3 is 15. And then we have f of 3, 3. Oh, it's right between them. So we have to look at which piece it will be in based on this. This says if x is equal to 3, we use that. So that'll be 27, negative 27. All right. Let's do one more. All right, pause the video and try that one. And we're dividing up the number line with negative 4 and 12. To the left of negative 4, we're going to use this. Between them is this function. To the right of 12 is that function. And if we want f of negative 4, that's where it's divided. So we have to pay attention to, can x equal negative 4 here? No. Can x equal negative 4? Yes, so we're going to use that. 6 minus negative 4 squared. 6 minus 16, we get negative 10. F of 12 So we look at 12, that's another of the boundaries. So we see that if x equals 12, it's going to be this. And then there's no computation to make. We'll just throw in one more. F of 3. F of 3, so we look for that on the number line, is right there between -4 and 12. So we need to use this function, 6 minus 3 squared, 6 minus 9, -3. All right, and now we have a difference quotient, evaluating a difference quotient. All right. So we're going to find each of these values for each of these functions. This is the difference quotient. It's something used in, well, this form is used in calculus, but this is really ends up just being the slope formula, y minus y over x minus x. So it's used throughout. Every time you use slope, you're really using this. So let's look at f of a. F of a means copy f and leave a space for the x, but instead of the x you write an a. F of a plus h, copy f, leave a space and put a plus h. And then we have f of a plus h minus f of a over h. F of a plus h is there. F of a is there. And we're done. Okay, so let's try this one. We'll have f of a is going to be copy f 2 over 5 minus a space. In the space you put a. Then we'll do f of a plus h. Copy f 2 over 5 minus a space. And we'll do a plus h. Then f of a plus h minus f of a over h equals, and now we just copy f of a plus h minus f of a over h. So f of a plus h, 5 minus a plus h, and then we have, that's f of a plus h minus f of a. And then we have to just get rid of the complex fraction. We don't want to have these fractions in the numerator. So what we have to do is get a common denominator. We're going to multiply this fraction by 5 minus a over 5 minus a. We'll multiply this fraction by this denominator. So here's what we have so far. So let's multiply 5 minus a plus h, 5 minus a plus h. So I'm going to multiply this denominator by that denominator, and then we'll multiply over here like that. And here we have 10 minus 2a there. Over here we're going to have minus, that'll be a 10. This is negative 2 times negative a, that's going to be plus 2a. And we have negative 2 times negative h, negative 2h. And then the denominator is going to be, for now I'll just write 5 minus a, 5 minus a plus h. We can simplify the numerator. 10 minus 10, 2a minus 2a, 2a minus 2a. So we end up with just negative 2h. And, oh, that is supposed to be a positive 2h. We have a negative 2 times negative h. So we're going to have plus 2h over 5 minus a, 5 minus a plus h. And almost forgot one thing, and that is this h right there. So I should have written this whole thing over h, this whole thing over h. So we're dealing with all these fractions. You need to remember the h is there. This whole numerator is this numerator, and there's still an h under it. And then we simplified that, and we still have an h under it. So now we can, instead of dividing by h, let's multiply by 1 over h, and it'll cancel that. All right. Okay, pause the video and try those problems. So let's just replace the x's with an a. And let's replace the x's with a plus h. Remember that this is not a squared plus h squared. We have to distribute it. A squared plus 2ah plus h squared plus a plus h. And that's going to be 2a squared, 4ah, 2h squared plus a plus h. Then when we have the difference quotient, we're just going to copy this. F of a plus h, and then we're going to go minus 2a squared plus a and over h. So now we want to have 2a squared. Let's just write plus minus minus 2a squared minus 2a squared, a minus a, and then we're left with 4ah plus 2h squared plus h. And everything in the numerator has an h with it, so we can factor that out. Cancel, and we have 4a plus 2h plus 1. All right. And the last one. That was f of x equals 3 over x plus 1. And we have to do f of a will be 3 over a plus 1. F of a plus h. 3 over a plus h plus 1. And then we have f of a plus h minus f of a over h. So we have 3 over a plus h plus 1 minus 3 over a plus h. So we need a common denominator here, and let's multiply each side by the other denominator. So we're going to have a plus 1, that'll be a plus 1 over here, a plus 1 there, over here, a plus h plus 1, a plus h plus 1. So we have 3a plus 3, and minus 3a minus 3h minus 3. This is all over a plus 1 times a plus h plus 1, and it's all divided by h, so I'm going to multiply by 1 over h. Alright, now we have 3a minus 3a. We have 3 minus 3. Those are all equaling 0. What's left is a negative 3, but we have an h and an h here, and those will cancel. So we have negative 3 over a plus 1, a plus h plus 1, and we get, we'll stop there. Okay, and that's the end of this lesson.